All right, we'll get started. So last Thursday, we spent time talking about the fact that often the decisions we're making with respect to what kinds of consistency models we want reflect political decisions. They reflect non-technical decisions. The term political might be a little loaded there, but the point is that often when we are building distributed systems, the things that are driving the technical choices are not technical issues. And one of the things that makes it a little more complicated is the fact that trying to explain to people the technical issues when they're simply sitting there trying to solve a business problem, it can be itself challenging. I don't know if you've ever had any of those conversations, but one of the skills that I would encourage you to try and develop over the years is translating tech into non-tech, explaining to business people what the trade-offs are. Because salespeople have this tendency to want to sell things. And they will tell the customer, prospective customer, whatever they need to in order to close the sale. And then they come to the tech people and say, now you have to deliver. So I'm not going to do this exercise. I'm just going to basically note that, in fact, this is really what happens in the real world when you're really talking about real projects. That people are often unaware of the complexities of what we're talking about, of the, well, we should just be able to do this. I took a class, 20 years ago, and we learned draft, which isn't quite possible because draft is only 12 years old. But then again, I also see recruiting ads for people with 3 to 5 years of agentic AI experience. And I'm like, are they planning on hiring anybody from Earth? So the reality of this, and this is I'm going to tie it back into the way we think about how do we recover from failures. Our failure here is that coordination itself is inherently expensive, and trying to explain why it's expensive to other people is a challenge. I don't know, maybe you haven't picked up on the fact that coordination is expensive. It's pretty easy when you're doing it on your laptop with a couple of simulators. It's not even that bad when you're doing it inside of the same data center and you're just simply doing replication across racks. As you start doing it across data centers, that gets trickier. When you're sitting there working in a company that is using multiple data centers, let's go to the paranoid end. We will spend money to make sure that this thing works right. And you don't replicate everything to the same data center. You don't replicate everything to the same service. What is the risk of using any cloud-based service? Now we're back. We're still talking about failure. What could possibly go wrong? Anybody ever notice any cloud services going down at all? Amazon just had a big powwow, big meeting of the whole company talking about how AWS was not meeting their reliability goals because they were having problems deploying code that was not properly vetted because, of course, the same people who are now complaining about the not properly vetting are the people who decided that they should actually require everyone use lots of AI. How many of you used AI? One person. Oh, okay, I can see the hands over there. Good. Oh, okay, about. So, right. How many of you had it do something you looked at and you said, that's just dumb? And that's the learning experience here. You have identified a failure condition. You've identified a failure state. I thought one of the most interesting comments that came out of class right at the end or afterwards last week was somebody said, that they used AI for all their classes, and this is the one that it didn't do a very good job on. And if the AI can't understand it, why would you expect management to? So today we're going to challenge this basic idea of coordination. We're going to say maybe there are ways of solving this problem that are not related to coordination, but in fact to restricting what we're doing so that structurally we get the right answer. And what you can do is you can just look at this and say, from a mathematical perspective, anything that I can compose could potentially be something that I don't need to coordinate, because the order of the operations doesn't matter. Well, assuming that the composition is properly restricted, and that's really going to be the key, that properly restricted. All the consensus protocols we're looking at, they all have this commonality, right? We need a quorum. We need a quorum to read. We need to have some sort of guarantee. We need to understand what we're doing in order to ensure that we're looking at the most recent decision. And I keep coming back to the Martian data center, but I think that the Martian data center example, I really like it because it underscores the difference between linearized consistency and sequential consistency. Because the client on Mars can keep reading the local Martian copy of the database, even when Mars can't be talking to everything remotely, because the local copy is presenting a sequentially consistent version of the data, even if it's not linearly consistent. In other words, somebody reading on Earth is seeing a newer version of the same value, but that's a lie, because that's the propagation delay. And it's like, try to explain that to people. That's why I like that example. It's like, it makes it much easier to see that, because normally when I'm sitting here, even I have to think about it. It's like linear versus sequential. Linear, everybody has exactly the same view. Sequential, we all have the same order that we observe things in, but you might see something before I can see it, and that's okay. But that's what makes this all expensive. We end up with a lot of messaging. We end up sending messages here and there, and that is one of the things that when you sit down and you look at actual protocol implementations will be very confusing, precisely because the protocol they will implement is going to incorporate all sorts of optimizations. Where can we combine two messages together? Well, combining two messages together doesn't make it obvious why they're doing it. It in fact does exactly the opposite. It provides you with job security, because you're the only person who understands why this is still the equivalent. Anyone else who looks at that is going to have to disentangle it. And that isn't necessarily clear. We need quorum in order to be able to be reachable, because otherwise we can't provide availability guarantees. We have this complexity around leader elections and ballot ordering, and the really tough one that we've mostly punted on, which is why I make you do all of those really fun readings. I mean, Petrov and Klutman are both really good books. They are really good. When I first looked at them, I said, these are awesome. But they're not necessarily what you need in order to just understand what we're doing here. Those are the kinds of books that when you're building these systems, you're going to go back and you're going to look at. And at least you'll say, wait a minute, Petrov talked about this. You know, how do you detect when someone else is dead? How do you recover state? How do you build gossip protocols? Or maybe you'll never build these systems. Maybe you'll just simply decide that what you really want to do is build lots of corporate apps that make it really hard to cancel recurring subscriptions. We all know what we're talking about there too, right? It's literally like, I use it on Claude all the time. I say, oh, so you wanted an honest corporate job where the CFO says we need to decrease the number of people who successfully cancel. And you know, the sad part is Claude knows exactly what I'm talking about. Oh yeah, you're right. I know that pattern all too well. But great. So what could we do instead of using coordination to restrict the class of problems that we're trying to solve to only those that don't require coordination? Is that even possible? Can we do this structurally? So we don't want a leader. We don't want quorum. We don't want ballots. We just simply say, hey, everybody takes rights where they are, and then they replicate those rights out across the cloud, across the other replicas. And this was first proposed in 2011. It is based upon a concept of what is called a lattice. Now, if you are not a mathematician, the way to think of a lattice is exactly where I started early in this term, where I said, look, there's lots of different paths from point A to point B in a network, because we can just simply move the way that packets are ordered around. We can drop some packets here. That's what DSLabs does. It simulates this large search space. Lattices are the set of paths that all get from point A to point B, regardless of how they exactly do it. And that's the mathematics behind the consistent cuts. That's the mathematics behind why pretty much everything we talked about in this class actually works. The FLP theorem, which is definitely math, is an argument around how you construct a lattice that guarantees that it has always at least one more path to traverse than you're willing to wait for. The way we broke FLP was in essence to bound that. We said you can only have this many steps. One more step than that, and no, sorry, your packet's dead. That's a TTL. That's exactly what time to live does. It says you can only go through this many hops. In Spanner, they use time. They use clock time. They're both clocks. Whether it's a timestamp from our crazy little celestial clock, or it's a Lamport monotonically increasing sequence, which is just the counter. An event ID, an operation ID. We use both of them all of the time. So, we're going to actually create a particular kind of lattice, a joined semi-lattice. And here is the interesting property of that. It says that any set that has an operator on it where any element in the set can be joined so that it's commutative. It doesn't matter the order in which you do the operation. Commutivity is really important. That's really one of the key properties here. It's associative. It doesn't matter the order in which you perform it across three things. And performing the operation with itself gives you what you started with. So it's an identity. This is very abstract, right? This is an abstract definition of a mathematical object. And what it tells us is if we can actually find sets with these properties, and really the key is the operator. You notice the binary operator, so it takes exactly 2. Anything that we can compose this way, anything that fits this criteria, can be used to construct this joined semi-lattice. The order in which we perform these mergers doesn't matter. That's really what this is saying. I don't need consensus now. I just need to eventually find out about what happened. And I can apply it then. This is eventual consistency. This is really the core definition of eventual consistency. And this tells us that my little joke about, it's eventually consistent but never consistent really does fit, because every little node is sitting there applying these things in every possible order, and you don't really know when it's all converged. Well, we could probably fix that. You don't really know when it's all converged, but it's not going to be easy to do. So when we have replicas that are each accepting inbound writes, it doesn't matter the order in which those occur or relative to the writes, we always end up with the same outcome, because that's the whole point. A union B union C is the same as, B union A union C as C. It doesn't matter the order. It makes no difference. There's no ordering dependency here. Now that's a pretty strong property. So we've restricted the space of operators that we can actually choose here. Often the operators are logical operators, not physical operators. And some things just don't work right. So this would allow addition, for example, but it doesn't work well with subtraction in addition. So your operators are all going to have this property. And we're going to solve that subtraction addition problem in a different way. So in lecture 10, we talked about the quorum intersection property. That's what makes consensus right. So the question here now is, what property here replaces that intersection property? What guarantees that we are eventually going to converge? And this one I will do. We'll take 2 minutes, talk about it, and see what you come up with. All right. What'd you come up with? What is it that makes a difference then? Why don't we need consensus? Did anybody use CRDTs?
Through the fact that we can always join them and then they'll be consistent. consistent no matter what.
So all we need to do is just get the messages. We just need to know what the events are. That's, in essence, why this works. Because we have the same problem with Paxos. In order to get all the replicas up to date, eventually all of the messages have to be delivered. The difference here is that we also have a different consistency guarantee. Paxos is giving us sequential consistency. This is giving us eventual consistency. So we still have consistency, it's just a weaker model of it. On the flip side, it might be weaker, but it's way, way easier to implement. Provided that you always get those messages at some point. If you don't get those messages, then that's a separate problem. This is where those supplementary materials come into play, because then you can get multi-version concurrency control and versioning and vector clocks and like other kinds of techniques that we use in order to detect when my copy's old. Those are repair techniques. Those are make sure that the messages get delivered techniques. So here's a really simple example, the grow-only counter. So we have 3 replicas, A, B, C. Each replica maintains a vector of counts with 1 entry per replica. So super simple model, right? We've just got one value again. So at some increment I, the vector of I, we just increment it. We just add 1 to it. And the value then is the sum over those. And when we merge them, what we do is we take the maximum of the values. Remember, so this would be if I was node C, I'd be taking the max over A and B for each I for those values. And the point here is this can only grow. It is restricted to growing. So it doesn't matter. Addition is really easy this way because addition does exactly what we want. We know that when you add to something, you can do it in any order. As long as you add all of the values, eventually you'll get to the same number, regardless of the order in which you do them. Then we get a nice little walkthrough here. So from replica A, at time 0, everybody starts with 0, 0, 0. Time 1, replica A bumps 1, replica B bumps 2, replica C bumps 3. And then you sort of keep doing this. Now there was no increment this time, so it didn't change. But there was an increment here. There was a double increment there. And then at the end, no matter what order these appear in, we always end up with the exact same merge at the end. So we're just delivering the messages in different orders. We're applying them in different orders. But when all the messages have been delivered, everybody ends up at the same place.
How do you bring ties?
There are no ties.
So you can't have RA increment second slot.
You can.
You can.
Right.
But so you wouldn't have 1, 1 in both RA and B.
Did we restrict it that way? Let's see. I think we can only modify our slot. So there's never a race there. This particular example, you're right. We eliminate the race possibility because of the way that we've constructed it. Each one has a separate counter. The interesting case is when you're composing a cross, at which point then you have to have a different construction. It would be a different operator. So this is a really simple example of an operator, but it's not defining the class of all possible operators. Usually when I see this, what actually happens is you always just add your, let's see, how do we do that? Well, you end up using a vector clock. And then you sum them all at the end, which is exactly what is going to happen. So I keep my number, you keep your number, she keeps her number, And then when we're all done, we all end up with the same values. We add them all up and we know what the total number is across the three. So that's us keeping separate copies of the same value in that instance. So the merge is maximum per entry. So each replica only increments its own entry. That's kind of going back to the point. The max never loses the increment because there's nobody goes backwards because you never allow it to roll backwards. And remerging with the same state doesn't double account because they'd be the same, either they're the same value, they have to be the same value. They're the same value, and that would give us max is still the same. So here we've made this structural, it's not a consensus decision, it's a structural decision. It says, I don't care the order you went through, you can only end up with one value at the end after everyone has reconciled all of the outstanding messages. So in Paxos, safety comes from quorum intersection and ballot ordering. Here, there's no protocol. It's just a simple function. The function has specific properties. The properties guarantee that we can do these in any order, and we'll always end up with the same result. Here's another example. The observed remove set. The problem is we have concurrent adds and removes of the same element. And the naive approach to the simple approach is very common. People do last rider wins. Without a global clock, how do we know which one is last? In this case, what we're going to do is we're actually going to build a vector clock. We're just going to do it in a very subtle sort of way. So each add also has a unique tag. And that is going to be our vector clock. So add inserts with a unique tag. Remove removes the tag part, but not, it removes all instances of the tag, even across the unique ones. So this is removing from all the ones you can currently observe. When you merge them, you take a union of all of the e-tag pairs and then remove where both sides of the tags have been removed. Let's see if I can do a better job of making that clear. So removes only kill adds it's actually seen. So if I haven't seen it added, I don't remove it from the set. And that's going to be the really important property here. Simple example, we have replica A, which adds milk to T1, and then it removes milk to T on T1, so it doesn't add anything here. Replica B adds milk to T2, and here that survives because the value and the tag survive. RA, replica A, saw an add and a remove, so it can remove both of them because they cancel each other out. So this is how we can actually do a subtraction. This is an inventory problem. I added one to inventory, I removed one from inventory. I added one to inventory. What do we end up with at the end? We end up with one in inventory. And the point here is that adding wins over concurrent removes, so we don't end up with a double decrement case. RB's add was independent of the add here, so that's why we have a different tag here. The result is the same. So why are the unique tags important in the OR set? What happens if you actually just track the element and don't put the tags in there? 2 minutes. what did you come up with? What happens if you just only track the elements and not the tags of the elements?
The same problems as we run into without the ballots. Like this.
Same problem that we ran into without the ballots. So what ends up happening?
Concurrency issues. Maybe two
Exactly.
people are trying to do something different, and then you have no way of determining who wins. What happens?
And this isn't, in fact, a distributed systems problem. It's a concurrent systems problem. It occurs in multiprocessor systems all the time. It can occur in a single processor system with threading, because you can literally see what's called the ABA problem, where I've seen it. I've actually observed it, had to fix it, make it work under high stress environments, which is we have a reference counted object. I'm trying to release the reference. You're trying to increment the reference. And I'm sitting there right at the point where my reference would make the object go away. And the worst possible thing is for my reference to make the object go away. I delete it, but you think you now have a reference on that object, so you keep using it. And that is a concurrency problem. And it's the same issue here. A simple way of fixing that is you just put a mutex around that operation. But a mutex, especially when you start working with distributed systems, becomes expensive, because now we are coordinating across nodes, and that was exactly what we were trying to prevent at the beginning of this lecture. We don't want to coordinate across nodes. We want to be able to do that without coordination. Now, in concurrent systems, the way I've fixed this in the past is that you do something a little tricky. You use an interlocked increment, or interlocked decrement, which relies on hardware to give you serialization. So I'm kind of cheating there. And then what I hold is a read lock. And I decrement it. And if my decrement says it's going to drop to 0, I say I don't have the right lock on the overall data structure. So I increment it again. I drop my read lock, I grab the right lock, and then I decrement it. And if it goes to 0 again, I've avoided the race. I've actually seen that happen in the real world and debugged it. And that is actually a performance optimization. It's not a correctness thing. It's just one of these things you realize, hey, wait a minute. The only transition I have to worry about is the one where I'm going from 1 to 0 and I'm going to delete it. This is more general. This is, how do I prevent this from happening over a network? And now in the network case, what's a really narrow condition in a multiprocessor system becomes a very common condition in the network, because now we have large windows where we could each be trying to do operations that conflict with each other. So the tags provide us with a way of denoting what was visible. I can undo things that were only visible to me because it's my tag. And this is kind of like ballots, isn't it? Because ballots, what we did was we used the node ID. And that's how we disambiguated. That's how we broke ties. So CRDTs are really useful, and I know that some people said they use them. CRDTs are really useful because they allow every replica to accept writes. This gives you really good multi-writer semantics. If you're trying to build for example, a shared document editing system, you're going to end up using CRDTs probably, because otherwise you're going to pay this huge overhead. Now maybe what you end up doing is building some sort of combined system where the CRDTs are across blocks. So you own a block, I own a block. And within our blocks we can order those things. That's basically just exactly this kind of tagging. The tagging says you get to control what you edited, I get to control what I edited, and then we can merge those all together. This is a huge latency win, because we are doing local writes. We're not round-tripping to someone to get permission to do something. It is partition tolerant because the replicas themselves can actually diverge and converge when the network yields. This is super simple to implement. Super simple. This is why CRDT-based systems, eventually consistent systems, this is why they're much cheaper to operate. They're easier to reason about. That doesn't make them trivial. Don't get me wrong. I'm not saying that you're going to build a CRDT-based system and go, oh, this is really easy. What you're going to find is there's still a whole bunch of edge cases and conditions that you have to deal with. I see your head nodding, so I'm guessing that you ran into one or two of those. Yeah. But this is strong eventual consistency. It doesn't matter the order in which things happen. Eventually, all of the systems will converge. But while the system is running, while it's actually making changes, while there are messages flying around and reconciliation protocols running, it's probably not consistent anywhere. When you're sitting there editing that Google Doc with somebody else, you're seeing what they're doing, but it's not in real time. It's close. It gives you that sense that it's real time. And anybody who's worked on those kinds of documents knows you don't use the same section that someone else is actively working on. CRDTs, on the other hand, while they're easier to implement, do not provide you with a large number of operations. The set of operators that can work under this semi-lattice join restriction is much smaller than the total number of operators. There is a fair bit of metadata overhead that you have to worry about this. So you're using tags, you end up with vector clocks, vector clock sequences. You end up with tombstones. Tombstones are when things get deleted. So you know that you're working. In real systems, people have this annoying habit of creating and deleting the same thing over and over and over again. And you need to know when the old version has gone away and the new version is new. And we use something called tombstone. There's no total ordering here. You get convergence, but there's no sequencing order. That's the whole point. It's eventually consistent, but not right now consistent. It's not strong consistency. Reads can be different depending on which replica you're reading from. So a single client could actually see different views. You cannot build bank accounts with non-negative balance invariants. You cannot build a unique username registry. There's just no way to enforce these kinds of constraints. You cannot build anything that requires test and set. If you require global knowledge, then you need consensus. There's just no way to get around that. If you can get away with local knowledge and eventually reconciling this, then you've got something you can consider using. So what ends up happening is that we now have this whole spectrum of CRDTs where the merge is always converging. We have a causal consistency where we can have partial orderings that these are commonly used in things like, like Facebook or Instagram or TikTok or pretty much anything where you're posting something and making it publicly visible. The propagation delay doesn't really matter much. These are fun because causal consistency gets hard when you decide you're going to delete something. When you're going to say, I changed my mind, I don't actually want to post that thing. And people will see it. It's the whole thing about, somebody puts a post on X. And then they realize that probably was a mistake and they remove it and it's never gone because someone saw it. Someone captured it. Because there are people who literally sit there on the fire hose, as they call it. I think they still call it the Twitter fire hose, even though it's now called X. And literally pull things off of it as fast as they can. It's one of the highest concurrent data sources that we know of. And then, of course, we get the strong coordination, whether it's two-phase commit, three-phase commit, Paxos, Raft, U-step replication, so on and so forth. I'm not going to do this. I'm looking at the aggregate information. So Code Freeze was Friday night, and I've been busy since then. So interesting aggregate information, not individual repos. The trends that I thought were particularly interesting are, some of these are really well done. I would say about a third of the repos show pretty strong results on all axes. Quite a few people, and this is definitely the median, hit things a little more sporadically. I mean, the rubric was deliberately calling for you to make trade-offs because they're the exact thing that AI doesn't do very well. AI can work towards a single point rubric, but when you give it trade-offs that have to be analyzed, that's when it starts to get a lot harder to use it because it's less gameable. And then there's a couple of repos where things are a little bit weaker. Some of those, I mean, this is all still preliminary. I actually have some of those may be individuals, because if you're an individual in a group, there's data in here for both what's in your individual repo as well as your group repo. So the group findings will actually override the individual findings typically, unless your group was really bad. But hopefully that didn't happen to anybody. So that's why I said this is very preliminary, and I'm just looking at it right now going, what else do we have? Let's see. I have to look at that one. Apparently there's a fair number of unsigned commits, and I'm trying to figure out how that happened. It shouldn't have happened. So I need to go dig into that deeper. Some people, I thought it was really funny. One of the examples was somebody using the evidence log to put jokes in. So that was very creative. About a third of the class roughly said that they made minimal or no use of AI. 2/3 of the class said that they made much larger use of AI. And then what's interesting is that things spread out about how people used it. So some people used it for validation, so working on the designs that they used and built. Some people were focused on implementation. I think implementation might in some ways be the easiest way to use it right now. Some people I like this is a great quotation. I'd rather submit my own half-baked ideas than copy generated output without refining it. I mean, I have to agree with that. I basically almost never take anything that I get back from an AI and assume that it's correct, because it's like a really smart but lazy friend who will give you the answer that they can concoct right on the spot. And it sounds really plausible, but then you find out that it's kind of lame. And I see that all the time. So, the ledger is singing with honesty. I like that. That's a good quotation. A lot of people used the DS Labs infrastructure, which I thought was interesting. That's different than the classes before. So lots of repos with Paxos, several implementations of Raft from scratch, almost as many CRDT based, and then the trailing is the blockchain distributed ledger people. But there's a nice sampling of different implementations here. Not everybody used the DS Labs either. There's implementations in Rust, Go, Python, and React or TypeScript. I'm like, cool. Now you know why I'm not actually running this code. So I'm kind of curious, did people find the capstone challenging? Did you learn anything? I mean, what are you going to say? No? I didn't learn anything. I mean, and it's perfectly fair. You can say, no, I didn't really learn anything. I knew all this stuff coming in. I was just taking this class because it was going to be easy. So I'm in the midst of trying to get feedback. My goal is to have that feedback by the end of this week, and I might not quite make that, but you will have feedback. You might not have a final grade on that, but you will have feedback. So you have a pretty good idea of roughly where you're sitting. So you can make a decision on whether or not you want to write a design report, a design reflection. It's the same rubric. You are not changing the code in the design reflection. What you're doing is you're talking about what you would do differently. Because remember, my goal is that a lot of the benefit ends up coming from the places where things broke. I know this might sound strange, but when things didn't work the way you thought they were going to work, and you dug into it, and you figured out why it didn't work, then you actually learned something. And that's the kind of thing that's going to stick with you, versus a memorization for an exam at the end. And if you're going to go and work on distributed systems, those are the kinds of things that are going to create the very anchors that you need 5-10 years from now when you go, I've been here before. And I warned you, and I'm sure you probably were sitting there cursing and swearing about it. The rubric is deliberately vague. But it also is trying to constantly push you to balance between two things that if you optimize for one, kind of borks you on the other. And again, that creates exactly that kind of tension, because those are the real world trade-offs I keep coming back to over and over again. You make this easier, you make this other thing harder. CRDTs are great, but I'm pretty much punting on the repair part. The repair side of this is hard. It's allergies, it's that time of the year, right? All of the plants out there. So, if you have questions, let me know. Otherwise, I'm going to be busy through Friday getting feedback to you as quickly as possible. So, that's why I was like, I'll talk about this instead, because I think this is equally interesting. So, let me go back and look. Let me look at the prompt. All right, so we're doing multiple users sharing a shopping cart. Add and remove items concurrently. What merge operations do you want to make the list converge? What happens when, this is just basically a walkthrough of what I was just talking about, right? So if you use or set semantics, then you're tagging each individual operation, and removing kills the observed tags. Add wins because the remover never saw the add, so they didn't remove the one that the other guy added. Here's an interesting question that comes up. What do you do when you have products with the same general name, but they're different types? Comes in different sizes. This becomes a design decision you'll have to deal with. It doesn't actually support exact quantities. This is kind of interesting because that is exactly an example where CRDTs don't work. So we've spent a lot of time talking about Paxos. Now I'm going to touch on Raft. And it turns out that Raft is Paxos with just a few little differences. Paxos, Raft, view stamped replication, Pachyl Byzantine fault tolerance. They are all state machine replication services. Blockchain, state machine replication. What we're trying to do is end up with a linear sequence of events that can be used to reproduce exactly the same outcome regardless of who performs it. That requires a deterministic sequence on a machine that only will process them with one possible outcome. So this is getting rid of Markov models, for example. These are not going to work with stochastic systems because stochastic systems don't lead to the same outputs. You're familiar with stochastic systems? Okay, great. So that made sense. I'm sitting there talking about it, and I'm like, if they don't know what stochastic systems are, that will probably sound like a foreign language. And you might know what stochastic systems, and it still sounds like a foreign language, but that's a different problem. So, all the practical consensus systems end up with some sort of a leader election, because leaders are efficient. Almost always, except when they're not. They do log replication. That's what the leader's doing. It's sending the log entries to the other nodes in the system. Once enough nodes have received it, then that becomes a hardened decision. And then we have to deal with configuration changes. Configuration changes are a leader fails. Configuration changes are we actually add or remove nodes from the setup. In the first design lab, that's exactly what you were doing. That was mostly about dealing with configuration change. And you probably didn't fully realize that, but that's exactly what we're doing. That's why we had a view server. That view server was how we could add a node, a primary, or a backup, and how we could promote a node, your backup to a primary. Or even how to remove them. So Paxos, Raft, ViewStamp Replication, and Zookeeper, ZAP, are all implementations of variations of this. There are differences, but the differences are subtle. It's not the big model that's different, it's the implementation that varies. So, how we name things. We like to use different terms for the same concept. How we constrain our leaders, what we require for our log completeness, and how we deal with membership changes. So here's a nice little mapping table for these. An epoch maps to the term ballot in Paxos, term in Raft, view number in ViewStamp Replication, or epoch in Zookeeper, ZAP. The proposer, who's proposing the change, is a proposer in Paxos, a leader in Raft, a primary in ViewStamp Replication, and a leader in ZAP. Who stores it? Acceptor in Paxos, server in Raft, replica in ViewStamp Replication, follower in ZAP. A leader election is phase 1, or a request vote, or a view change, or a recovery. Normal operation, phase 2, append entries, normal op broadcast. In fact, actually, if you take Paxos and you put Lamport's configuration change on top of that, I think you end up with 3 turtles, not 2. But you can stack as many turtles as you need. The safety variant here is that the chosen values are never overwritten. Once we've made a decision, we don't change it. That's why I use the what's for dinner example, because what's for dinner tonight can't be changed tomorrow night. You can make a choice for tomorrow night, but yesterday's dinner, it already happened. You can't undo that. And that's the kind of strong guarantee we want. All of these are some sort of quorum intersection. Flexible, the Heidi Howard's work, or most of the time it's just majority because that's easy and that's all you need. Majority is the common example you will see, but it's only one instance of what you can actually do when you realize that this is always intersection in a set. So we just change the names. But this will help you see that we're studying the same thing over and over again with subtle differences underneath. Did anybody implement Raft? Okay. Does this make sense to you? Yeah. So maybe you didn't think about it when you were building the Raft implementation, but now when you look at it, you're like, oh, okay, I can sort of see that. Raft was chosen not because it was a better protocol, but because it was supposed to be easier to understand. I'm not entirely convinced that's true, but that's fine. So, Paxos Phase 1 is the Raft election, and you can see that here. I'm not going to read the slides. You can read them Raft just adds this constraint that servers only vote for candidates whose log is at least as up to date as their own. And this is interesting because this is how Raft makes their recovery easier. Paxos doesn't do that. Paxos does this differently. It says adopt the highest ballot value. Remember when the acceptors came back, they sent back the highest ballot that they had already accepted? There you go. And that's how Lamport solved that problem. So it's the same problem. How do I know what the last decision was? It's just implemented differently. That's why I say there's like these little differences. It's not a huge difference. Conceptually, it's doing the same thing. It's just achieving it slightly differently. In Paxos, we have a proposer that sends an accept to the quorum. Acceptors accept if that ballot number is greater than equal to their highest promise. And then the value is chosen when a quorum accepts ballot B for value V. Raft uses this append entries, where what you're doing is you're sending a list of all of the entries that are above. So yeah, I voted for this one and this one and this one and this one, and I'm going to send all of those things. And that entry then becomes committed when we have replication to a majority. Majority is just a restricted form of quorum. If you haven't looked, you might be able to actually go and do non-numeric quorum in Raft, but that's not the default protocol. They're just using n+1/2. Similar mechanism. Each of these has a term limit, and that term limit is defined by the ballot or the accept. Ballot accepts, right. So these are implementing the same thing. Right. This we've actually talked about before. The Raft idea is slightly new. So you get an advantage on this one because you already know the answer. We'll do a 2-minute here just so you guys can talk through, because I think the Paxos one is the one I want you to see if you can still remember.
It's just the bug. Yeah, I feel like it's the stroke of the so when you vote for people where it has so it's like assuming the last ballot.
All right. In Paxos Suite, a new proposer has to adopt the highest ballot value it's discovered in phase 1 in Raft. A new leader doesn't need to do this step. Why not? What is it the RAF does differently here?
Well, we have a check when we're doing the candidate votes to make sure that we only elect the leader that's already elected. So it's not, it already knows about whatever the last highest accepted one is.
Right, so we only accept leaders who are already, who are in the quorum already. So they know what the last decision was. And that means that we don't have to catch them out. Remember that horror condition I described before with Paxos, which was a new node comes online, recovers. A new node recovers with an empty database. And now we have to get it all caught up. How do we do that? We literally have to copy the entire database over before we can let the new leader take over. Otherwise, the new leader can't propose anything because they don't know what the state of the world is. And this is a simplification of RAF, in all fairness. Yes?
Does RAF not have that same problem Paxos has? Like the new...
RAFT solves it in a different way, right? So RAFT, so the point is that RAFT only will allow a new leader to be elected if it's already in the quorum. In other words, the leader has to be in the intersection already. And since it's in the intersection, it knows what the last decision was. Paxos didn't know that because the proposers could actually be behind, but still propose themselves. So in Paxos, we have a discovery phase, then we pick out the highest value. This is what they combine here. Because only leaders who know the highest value are actually allowed to win the election. And how do we guarantee that? We send the information back in the election itself. So you could argue that this is not a different protocol, it is an optimization because we are combining two messages together, but I don't think it's quite that simple, but it's close. It is in fact the same mechanism, just with a different implementation. New stamp replication was introduced in 1988. It predates Paxos by a decade, and it predates RAFT by almost 3 decades. 27 years. 26 years. So, in Oki and Liskov's review stamp replication, a view was pretty much, well, no, let's not go there. A view is just an epoch with a designated primary, so there is a leader. The primary is the leader in this case. In a normal operation, the primary broadcasts operations, the replicas execute them in the order in which they are received. When a view change occurs, the primary is, because the primary has failed, the replicas elect a new primary, they reconcile their logs. And the reason they use a log reconciliation at this point is because that's essentially, it's not even essentially, it's how they are reading quorum. Reconciliation here means I look and see what a quorum have, and I know the most recent value there is the value that should be that wins. It should be in that position. This is actually simpler to implement in some ways than Paxos, in many ways than Paxos. It is different than RAF, but not radically different. It's almost the same protocol. And it's been around for a long time, and it's been used. I've seen it implemented because it was highly effective. I would say that one of the key things they do in view-stamp replication is that they elect their leader based upon network address. And that's how they solve their leader election protocol. The leader is the one who has the highest IP address or the lowest IP address, whichever one it is. I think it's highest. So when we put all of these together, what we end up with is this whole set of different ways of achieving various kinds of consensus. We have CRDTs, which are not coordination-based. We have causal consistency-based, where we maintain ordering, but we don't rely, or we don't require strong consistency. We're not looking for linear consistency. And then we get into the consensus, where we have sequential consistency or linear consistency even. And these all span. Actually, this is not 1989; it's 1998. Missed that. And I think the interesting point to make here is that these aren't competing solutions. They are solutions that work well for different kinds of problems. And often when you build real-world systems, you combine these to come up with something that uses more than one, depending upon the particular case. So if you're writing a collaborative editor, you can do text editing with a CRDT, but you might want to do file permissions at the consensus level. User presence can also be done with a CRDT, where you keep track of when people are alive, because you're trying to do dead detector. Account management, on the other hand, almost always requires consensus, because you need some sort of unique username. Now, having said that, I could point out that you could always just simply use a UUID, which is now a distributed name generation protocol. And that works fine too. Distributed databases often are used for various kinds of things. Like you were doing a shopping cart, you put session data, you put that into a CRDT. You don't need strong consistency for that. You need something that basically just works most of the time. Account balances, on the other hand, inventory, things that are tied to money. That's where you want strong consistency. So that's where you're going to end up using some sort of a consensus-based protocol. Speaking of consensus-based protocols, I will note that both practical Byzantine fault tolerance and blockchain protocols are in the strong consensus category. But they are a special case of strong consensus that is Byzantine fault tolerant. In other words, we can have bad actors. And I mean, blockchain in particular is really geared towards bad actors, whereas practical Byzantine fault tolerance is often geared towards just dealing with situations where the networks are unstable, where things can go wrong, packets can be corrupted. So if you're building a system with both CRDTs and consensus replicated state, and a developer proposes using a CRDT for a likes counter on posts and consensus for the post content itself, is that the right split? What failure would reveal a problem with this design? And of course, here's the big giveaway. What do you do when it gets deleted? I've already mentioned this. I said it's really easy to build this until you put delete in there. Because now your tweet on X, it doesn't work as well as tweet on Twitter, but okay, fine. You send out a message on X, and then you change your mind 30 seconds later. Now you're chasing your own messages across the internet trying to get them to go away. And that's when it gets hard. So the like counts are updated via CRDT. That's kind of funny. Okay, so I can actually be upvoting things that are no longer in existence. So there's a skew there. Maybe that's okay for your usage model. I don't know. So just to summarize, CRDTs are a structural mechanism for building eventually consistent systems that are way faster, way easier to construct, and often good enough. I give you the G-counter and OR set examples. There are plenty of other operators that you can consider. We have Raft, two-step replication, Zab, Paxos. They're all the same thing with small variations in implementation, but they're all doing roughly the same thing, which is they are linearizing the order of decisions, and they are used to replicate the state machine. So tying this all together, CRDTs use the joint semi-lattice as their safety mechanism. Consensus protocols are using quorum intersection as their safety mechanism, but both are paths through the same design space with different guarantees. and that's pretty much it. I mean, the reading can say required, but obviously, if you don't read it, no one will actually know. I'm not going to hold you to it. And the papers that I provided and suggested are hopefully useful background if you want to know more about distributed systems. At this point, we're pretty much winding up. Next Thursday will be the last class. I'm not going to do lectures next week. I'm going to be busy finishing up grading and getting ready for the next round of grading. So code's done. You have just under 2 weeks to decide if you want to do a design document. Based on what I'm seeing preliminarily, now again, I haven't assigned individual grades yet, but it's very likely that there's not many people who are in any risk of failing the class, which is kind of by design. I have a couple of people who basically just stop turning things in, but they're probably not here. So, any questions? All right, well then we will call that a wrap.